Hi, good day. So today we are to discuss torsion. In mechanics, basically torsion is the twisting of objects. So for example, we have this solid shaft. We are to apply, let's say, a clockwise torque on one end, and for equilibrium, a counterclockwise torque on the other end. So if we say torque, this is a twisting moment. So if we say moment, that is basically force times the lever arm. So if a body carries a torque, it experiences shearing stress. From our previous discussion, we use tau to represent shearing stress. So we have the equation of shearing stress for let's say, a solid shaft carrying a torque is equal to the applied torque multiplied by the rho. This is divided by J. So for example, we have a circular section and we apply a force tangential, for example, tangent to this circular section that creates the torque. So let's say this circular section has a diameter D. So basically, what is the equivalent of the rho? The rho will be equal to the diameter divided by 2, or simply equal to the radius. Then what is the equivalent of the J? So J is the polar moment of inertia. That is the moment of inertia with respect to x plus the moment of inertia with respect to y. But for a circular section, the moment with respect to x is simply equal to the moment of inertia with respect to y. That is for a circular section. And that is equal to, that is pi, the diameter raised to 4, divided by 64. So we can simplify the equivalent of the polar moment of inertia. That is basically equal to, let's say, pi d raised to 4 divided by 64 plus pi d raised to 4 divided by 64. We have the polar moment of inertia for a circular section is now equal to pi, the diameter, raised to 4 divided by 32. So that's why we can simplify this equation. For a solid circular shaft or a solid circular section, we can simplify this equation. So let's say we have the shearing stress is equal to the applied torque. What is the equivalent of the rho? We can have it as the diameter divided by 2. Divided by, we have the polar moment of inertia is pi, the diameter raised to 4, divided by 32. So simplifying that equation, or simplifying this equation, we'll be having the equivalent of the shearing stress. We may cancel one of the d. So this will now be d raised to 3. So 32 divided by 2, this will give a value of 16 multiplied by the torque divided by pi times the diameter, pi times the diameter raised to 3. So this is our formula for a solid circular shaft for computing the shearing stress. So if we are to compute for the angle of twist, so since torsion, again, we are to twist objects, so it will it may result to an angle of twist. So we have the formula for angle of twist is equal to the applied torque, or the length of the material, divided by the polar moment of inertia multiplied by the modulus of rigidity. So take note, this is in terms of radian. So if we are to express the angle of twist in terms of degrees, so we are to multiply this one to 180 degrees is to pi rad. This is our equation for the angle of twist. So let's have an example. So let's have this example. For example, we have a solid shaft with a diameter of 2 inches. So it carries a torque at A, that is 900 pounds-foot counterclockwise. At B, we have 400 pounds-foot clockwise. So the given modulus of rigidity is equal to 12 times 10 raised to 6 pounds per square inch. So these are the requirements. So we are required to give the torque diagram, the shearing stress for segment AB and the shearing stress for segment BC. Okay, for the first one, if we are to draw the torque diagram, okay, so let's have an analysis or equivalent analysis for the torque. So we have a counterclockwise rotation for torques. This is positive. So if we are to analyze them as the way we do with axial forces, okay, that is equal to, okay, a force to the right is a positive force. Okay, that is the equivalent. Alright, then for a clockwise rotation, we assume this to be negative. So when it comes to forces, that is an arrow to the left. This is negative. So therefore, we can give the equivalence of these torques. 900 pounds-foot, that is counterclockwise. So we assume this to be to the right, the same as torque. We are just placing an equivalent symbol for an easier analysis. So this is 900 pounds foot. Then at B we have that is 400 pounds foot clockwise, so it should be to the left. So it's the same as 400 pounds foot. Okay, so for example, we are to determine this the reaction on this fixed support. We may do the summation of torques. For the summation of torques equal to 0, we assume torques to the right to be positive. So let's say this is the torque at C. I'll be assuming that it is to the. I'll be assuming that this the torque on the fixed support will be to the left. Let's say this is the torque at C. Okay, so we have torque to the right to be positive. That is, we have 900 that is 900 pounds-foot, then minus 400. I'm assuming that TC is to the left, so that is minus TC equal to 0. So we'll be having the torque on the fixed support is equal to 500 pounds-foot. And since this is positive, we have a correct assumption. Its direction should be to the left. So if we are to place that torque reaction, it should be a clockwise torque. 500 pounds foot. Okay, so it is a 500 pounds foot. If we are to replace it with an arrow symbol, that is to the left. Okay, so we are now ready to draw our torque diagram. Okay, so we may start on the right end of the shaft. So we have 900 pounds-foot to the right. So that is a positive torque. So we are using we are starting from 0 to a magnitude of, let's say, 900. So 900, that is a constant value up to point B. Then at point B, we have a torque of 400 to the left. So that is we are to do the summation of torques. 900 minus 400, that will give us a value of 500. Then 500, a constant torque up to point C. Then at point C, again, we have a torque that is 500 to the left. So 500 minus 500, that will give us a value of 0. So as you can see, the torque for the entire span is positive, which means we have a more value of counterclockwise torque compared to clockwise. So we have the torque or the net torque for segment AB is equal to 900 pounds-foot, and the net torque for segment BC is equal to 500. That is equal to 500 pounds-foot. So we are now ready to compute for the shearing stress. So for the shearing stress is basically equal to the applied torque, the raw, divided by the polar moment of inertia. But for a solid shaft, we can use the equation 16 times the applied torque. This is divided by pi d raised to 3. So computing for the shearing stress for segment AB, what is the applied torque for segment AB? This is equal to 900 pounds-foot. Then multiplied by, we are using this equation instead. So this is 16. This is 16 times the torque for segment AB is equal to 900 pounds-foot. This is divided by pi. We have a diameter of 2 inches raised to 3. So to be consistent with the units, we are to convert this feet. So we are to multiply 12 inches is to 1 foot. So we'll be having what is the value of the shearing stress for segment AB. That is the same as 16 times 900 multiplied by 12 divided by shift pi multiplied by 2 raised to 3. So we'll be having a value for the shearing stress for segment AB equal to 6,875 6,875.494. If we are to do unit analysis, cancelling feet, this is inches. This is supposedly inches cube. Cancelling 1 of the inch, this will be inches squared. So pounds per square inch. This is the same as PSI. So this will be our answer for the shearing stress for segment AB. 6,875.495. For the shearing stress for segment BC is equal to 16. What is the net torque for segment BC? That is equal to 500 pounds-foot. Multiplied by 12 inches is to 1 foot. Then all over, we have pi. We have a constant diameter that is 2 inches. So we'll be having the value of the shearing stress for segment BC. That is 16 times 500 multiplied by 2. Supposedly this is divided by pi divided by 2 raised to 3. So divided by pi divided by 8 raised to that is 8, 2 cubed. So we'll be having a value of shearing stress for segment BC 1,819.719 pounds per square inch. So this will be our answers. So the shearing stress for segment AB, the shearing stress for segment BC, and our torque diagram. So for example, we have an additional requirement. We are required to compute for the rotation at point A. So rotation at A, so as you can see, point A is the free end of the solid shaft. So how do you compute for the rotation at that point? If it is the free end, that is basically equal to the summation of the angle of twist. That is the summation of the torque multiplied by the length divided by the polar moment of inertia times the modulus of rigidity. So since we have a constant diameter and a constant modulus of rigidity, we can factor that out. So we have the rotation at A is equal to, we are to factor out the constant denominator, that is the polar moment of inertia, modulus of rigidity, multiplied by the summations of the torque multiplied by their corresponding length. So we have the rotation at A is now equal to, this is 1 all over, or 1 divided by, our polar moment of inertia is pi, a constant diameter 2 inches raised to 4, so that will give us a unit of inches raised to 4 divided by 32. Multiplied by the modulus of rigidity, this is 12 times 10 raised to 6, psi, pounds per square inch. So we are to multiply. So the torque for segment AB is 900 pounds a foot. Then multiplied by the length, 5 feet. Then plus, for segment BC, we have a torque of 500 and a length of 3 feet. So they are both positive based on our torque diagram. So that is plus 500 pounds foot multiplied by 3 feet. So the unit of our numerator will be in terms of the pounds, feet squared. So if you are to do unit analysis on our denominator, this is inches raised to 4. So we are to cancel, this is now inches squared. So this is pounds, we are to cancel pounds. If this is now feet squared, we are to multiply. This is multiplied by 12 inches is to 1 foot. Since this is a feet squared, we are to squared. Raised to 2 for this term. So let us now determine the equivalent of the angle of a twist for A. So by the way, if this is already inches squared, we are now cancelling the remaining inches. That makes this unit in radian. So we have the angle of twist, that is 900 multiplied by 5 plus 500 multiplied by 3, multiplied by 12 inches squared, divided by the polar moment of inertia, that is shift pi of 2 raised to 4, divided by 32, then divided by the modulus of rigidity, that is 12 times 10 raised to 6. So we'll be having a value, the rotation at A is now equal to 0.0458 radian. If we are to, if you want this value to be in degrees, this is multiplied by 180 degrees is 2 pi rad. So we have the angle of twist at point A in degrees. So we have 0.0458 multiplied by 180 degrees, divided by pi. So the rotation in angle is 2.624 degrees. This will be the rotation at point A. As you can see, if this is positive, which means the rotation is counterclockwise. This will be our solution for the computation of the rotation at the free end.